Correct. Scientific method. So let's start off with just discussion of what is science? What does it do for us? What does it look like? There's some characteristics that I want you to keep in mind whenever you're doing science, whether in this room or if you're reading about science or at a class later on. Any type of science is involved in the study of the universe. We put it in different branches that are convenient for us, but biology, chemistry, geology, they're all studying part of the natural world. And sometimes then that allows us to extend it and do things ourselves which aren't technically natural, but we can use what we've learned for that. Curiosity. That's at the heart of any scientific endeavor. You want to know why or how something around us works. Back in ancient times, before we had developed this method of science to study these things, it often involved some sort of an explanation. There are lots of folk tales and legends that explain why is the raven black? Why is the fox's tail so bushy? And so they might have developed stories about that. There are lots of stories about how did the world begin. That was a big, big topic. And that's because people are curious and they want to know. Lacking the tools to actually study that, we would have stories that seem to make sense and often supported a way of life. So this is asked, you don't necessarily have to get these little boxes in. You may make a note if you want, but if the circled ones are enough, then I encourage you not to write everything down. It's got to be observable. Which means what? How do we observe things? I know all of you know at least one answer to this. And I will introduce you to something I call a die of power. This die has 12 sides, each numbered. We have 13 students. So the first time around, Felix will be safe. The second time around, I'll start counting again. It helps me encourage people who I'm confident have answers, but don't wish to give them. Dodged a bullet. Number 12. Let me get David. What's one way we can observe things? You can look at it. You can see it, right? Okay, what's another way we can observe things? Good, I'll get these names quickly. Patrick. Well, we already established seeing, so you're going to have to give me a different way you might observe things. So observe doesn't just mean seeing, so what other ways can you learn about something? Okay, let's remove your sense of sight. Close your eyes. Hold out your hand. No. I told you to close your eyes. And hold out your hand. Now keep your eyes closed. What did I put in your hand? How did you know that? You couldn't see it. Okay, so that suggests that's another way we could observe, right? Using our sense of touch. What else? Hearing. Smell. Using any of our senses, right? And we usually say we have 5 senses. we often have several more because we can sense heat, we can sense pain, lots of different things that are sort of related to others. Lots of different senses. So we can use our own senses. Is there any other way we might observe something? How might I observe how fast another car is moving?
By another car. Or by your car.
Okay, so I could compare it. That's sort of using sight. What if I was standing still on the side of the road? Maybe I had a little badge on my shirt. Technology. So specifically here, what would I be using? That would be in the car. Yeah, radar gun, something like that. But we do have lots of different types of technology that help us observe it or enhance our own senses, like microscopes, radar guns. There are things called electron microscopes that actually shoot electrons onto something and either see how many electrons go through it or how they bounce off of its surface. And so that's not technically seen, but we've developed ways to observe it even still. Astronomers use radio telescopes, so giant dishes that listen to radio waves coming in from stars. And excitingly, a couple weeks ago, astronomers in Russia were observing, and they got a very unusual signal at 11 gigahertz. That's a frequency of how many times does a wave change in the radio wave. And it was pointed at a star 95 light years away. And we don't know yet what that signal came from. It's possible there was a source of that, a non-natural source, or at least an artificial source on a planet orbiting that star 95 light years away. It's also possible, and perhaps more likely, that that is some highly classified military channel that the astronomers didn't know about, which would be a little disappointing to think that it's not aliens. But it's exciting nonetheless. It's at a place where, as far as we know, it shouldn't be. So observable could mean lots of different things, to get back to what we were saying. Not just using our own senses either. So we got to see or measure. It's rational. That's not a word that we use a lot. We've heard it more, I guess, in this political season than we normally would, but otherwise we don't normally hear it. We hear irrational more. If a person is described as irrational, what does that mean? Out of control. Doesn't make sense, right? Rational is the opposite of that. It means things have to make sense. Basically, this, then that, cause and effect. In science, we have to be able to see and prove this sort of cause and effect relationship in order for it to be viable. It's repeatable. That one we know. You have to be able to do this same experiment and get the same results. If you do the same experiment and you get a different result, there are two possibilities. One, there's no relationship between the things that you're testing. Or two, you haven't controlled something correctly. And it's actually a more complex problem than you're taking it to be. I think I've got one more. Yeah. And it's a process. It's something that we do over and over again to learn how these things are working. Okay, let's talk about that process, because this is the process that we'll see in every experiment we do. So this is a handout for the first experiment we'll do. We'll do it as a class, but it has all the steps so that you get used to doing it. And we're going to go down the line. We'll discuss what each section is, but you'll see these in every single one. So it's important that we know how these things get communicated to other people. Oop. Yeah. Okay, the steps. The first one is we want to determine what we're doing. This is called a purpose, or a purpose statement. This often, it's a written statement. Again, if you don't need the little thing down here, or if you can shorten it, I'm all for that. You don't have to write every word that I put up here. But it's a written statement that says, here's what I'm going to test. Here's what I hope to learn, or the relationship I want to learn about. Now, after we determine what we want to learn about, just naturally, we often form some sort of an idea of what will happen. What do we call that idea in science of what we think will happen? Okay. Hypothesis. So this is when we consider. Now, hypothesis, I don't have it on this page. I don't think. We have a very specific definition that you'll see throughout high school, and you've probably seen before in the last couple of years. What we're not going to say is that it's an educated guess. It really isn't. This is based, in a manner of speaking it is, but that is a very wishy-washy definition for what a hypothesis typically is. It's educated in the sense that we are drawing on our past knowledge. Guess is not a good word for that. So we'll use a prediction instead, and let's see. Yep, this is something, a definition that you will see on our first quiz and on every single exam that you take in this class. Because it's one of the most important things that I want you to know about. And this is the exact wording that you'll see. These are multiple choice questions. It says, which of these is a good description of a hypothesis? One of your options is this. So I want to hammer in that that's what it is. It's a testable if-then statement that predicts the outcome of an experiment. And it is based, here's the educated part, based on past experiences and knowledge. So this one, I do want you to copy down word for word, because you're going to see it exactly in that way on quizzes and tests. There is a special kind of hypothesis that is good practice to use because everybody who makes a prediction would like to see their prediction pan out. Nobody likes being wrong all the time. So it's a good practice then to make this hypothesis something called a null hypothesis. Null means no or none, in which you predict that the two things you are testing are not related. Now, we're sort of saying to ourselves, well, I wouldn't do the experiment if I really thought that. But this is something that keeps us honest a bit, because we aren't trying to prove ourselves right then. In science, just like everything else, if you look at a situation, you're going to often try and make it fit into what you think is already right. Scientists are not immune to this. They're perhaps better at it than an average person, but they're still not immune to it. So saying something like a null hypothesis and say, I don't think there's any connection. Well, that's more of an open way of looking at it and just seeing, I'd like to find out what the connection is, rather than predict something, maybe be shown to be wrong, and then feel like a jerk because of it. After we make this prediction, we're ready to set up and then perform our experiment. And so the next section there is experiment. This is where we test our ideas. I will have a list under this of some things that will appear in this section. You can shorthand these. You wouldn't have to write out all the words, but you will want to know the different parts that go in here, into this section. We would design and describe the experiment. So you could just say something like describe experiment. This is sort of your recipe, so if someone else is reading your work, they will know what to do in order to get similar results or to test the same thing. And at the very least, they'll know exactly how you tested it. We'll perform the experiment, and we'll record data and observations in it. So we're doing the whole experiment here. Whole experiment and recording everything that we measure directly from the experiment right in this section. So it'll have a data table, for example. We would not put things that then analyze that data. This is just, here's what I measured. After we perform the experiment, then we start taking a look at the data and figuring out what it means. So our next step is an analysis. What's going on? There we are. This is where we evaluate our findings. We make graphs. Let's see what else we do. If there are any calculations we need to do to see a relationship, we would do that. And we interpret what the data means. So this is now where we start looking at, okay, what did I find? Not necessarily how does it compare to my prediction, but it is what did I find? Last step. Now this is our conclusions. We see if we're right. So, did we reach the goal of the experiment? This is, especially when we're talking about our rockets, a place for errors, this goal of the experiment. A lot of people are thinking with rockets, well, did I go to 100 meters, which was my goal? That's never going to be the goal of our experiments. Our experiments are going to be exploring how does changing fin placement affect rocket flight. So our goal is actually, did we learn how fin placement affects the rocket flight? Not how far did our rocket actually go. So we want to actually check back with our purpose statement. That's where we stated our goal. And we say, did I meet the goal that I set out in the purpose statement. What did we learn and why is it important? This means how will it affect future experiments, especially when we're talking about our rockets? How are we going to apply this to make our rockets better? This is a challenging one too, to the experiment. This is saying, how could I do this experiment better and get more consistent or more believable results? In the case of our rockets, what it doesn't mean is, how could I make my rocket fly farther? That's not really the goal of the experiment. It's the goal of the whole project, but not of any experiment that we'll be doing. And are there any new questions? We've got just a few definitions that I want to go through, important pieces that we'll see throughout a lot of experiments. And then, so I think there's two more slides, maybe 3, but I think 2. And so we'll try and get through those quickly and then give your fingers a break. I'm on prudence. The next parts are how do we build an experiment, or how to do this. Variables is one of the important ones. A variable is something that changes. But when we're doing an experiment, we have to be careful not to have too many variables. If we change everything from one rocket design to another and it flies better, we won't really know what part of that made the biggest impact. And for our rockets, that will actually be really important to know, because you'll want to have the best fin size, the best fin location, the best amount of water in each bottle. All of those things really need to be tested separately in order to get a good view of how each of them affects the rocket flight and make the best rocket possible. So we break it up into 2 different varieties of variables. An independent variable is something you will change directly. We also sometimes called it a manipulated variable. But pretty consistently in this class, you'll see it as independent. Independent means it stands on its own. It's something that doesn't need another around it. Probably predictably then, if we have an independent variable as one, we'll also have a dependent variable. This is something that changes because of the experiment. So we change the independent variable and see how it affects the dependent variable, and sometimes we call this the responding variable. Now in any experiment, if we'll only ever have one independent variable. Very often we'll only have one dependent variable. But in any experiment, we're going to have lots of other things that could change about it. So if we're thinking about our rocket, maybe in one experiment you want to see how does the amount of water in one of the bottles affect the rocket flight. Well, there's millions of other things that we could change, maybe not millions, but lots of other things that we could change about the rocket, like fin size, or fin location, or the angle that we launch at. But if we want to learn about the amount of water and how it affects the rocket flight, we can't change those things. They would throw off our measurements because we wouldn't know, well, is it because of the amount of water or is it because of the angle that I launched it at? So what we have to do is we have to control the rest of those things. A control is something that is held constant and it doesn't change. It could change, and perhaps it will in a different experiment. But in a specific experiment, we only want the independent variable to change from test to test. Everything else will hold as controls. we've got last two really important definitions. So our first one was hypothesis, and you should probably highlight that or underline it with a colored ink or something. There are two other ones that we're going to see on every single test, and one quiz, at least one quiz. One is a scientific law. You've probably had some examples of these, like Newton's laws, the law of gravity, those sorts of things. This is a very specific statement that accurately describes some aspect of nature, and it's backed up with facts and many experiments. But it's very specific. So keywords here, I'd like you to write the whole thing, but keywords to remember: a specific statement that describes. I'm not going to try and trick you on these questions, you'll have multiple options, but I'm not going to change a couple words around and expect that you notice that. It'll be in this form, and there won't be one that's really, really close to it. But those are the prime words that I want you to remember with scientific law. Okay, so Newton's laws of motion. Theory is the other one, and theory is historically the hardest one for students to remember what it is. Probably that's because we use the word theory in common language. If you say, I've got a theory about that, or if a friend does, what does that mean? How do we normally use the word theory in typical? It means you have an idea. That is not what a scientist means when they have a theory. If they have an idea, it's probably more of a hypothesis. A theory here, if we built up a pyramid of science, we'd have lots of ideas down here, then we'd have some experiments, then we'd probably have some laws, and at the very top of that pyramid, the most important part would be a theory. Here, in science, a theory is a model that explains a natural phenomenon, and it's backed up by a lot of evidence and experiments. We take all of the information we have on a subject, we combine it, and we make this model that helps us understand things as best as we possibly can, given the information we have now. This is not something that necessarily will stay forever exactly in its form, because we can learn more about any subject. Think about the theory of gravity. We know a lot about gravity. We can describe how it pulls two bodies together that have mass. We can describe how it makes planets orbit stars, or moons orbit planets, and really orbit each other. So we know a lot about gravity. It's predicted that the force of gravity shares an energy between two masses by the exchange of something called gravitons. Gravitons are tiny, tiny, tiny particles that go back and forth. We have never observed those. So if we can someday prove that they either do or do not exist, or that something else exists, that would change our theory of gravity. It wouldn't change stuff that we encounter every day, but it would change the model and how we describe it. This is another good description. Here's what you'll see on tests, though. But a couple things to keep in mind, that often it consists of many laws, so there might be lots of specific statements that go into building up a theory that are all sort of interrelated. And importantly, it's the highest level of understanding that we have, not just an idea. And that's one of the main ideas I want you to take out of